Okay, good morning. So my instructions, are to do basic interaction of X-rays with matter, and basically from the first 3 chapters of the book. So my charge is not to do plasma physics, or I guess other speakers are going to do those things. And I thought that today I would do, this morning, I just do an overview of those 3 chapters with a few comments on other things, like sources. But so this is just an overview. And then the next lecture will be begin Maxwell's equations about the interaction, and about scattering, propagation and scattering. And then the third lecture is more on, we've worked ourselves up in lecture 2 to a refractive index, as indicated here. Where does this come from? What is that shorthand for? We'll have done that in lecture 2, but in lecture 3 we'll use that then for things like refractive index, reflection effects, a variety of things. And so that's where we're going. So this morning we'll talk about some really simplified atomic physics. It's not even atomic physics really, it's just nomenclature. How do we use these words? What do we mean? What are the outline of the processes? And then how do we use Maxwell's equations at very short wavelengths? And so that's what we're going to do. And it would be good if you ask questions, and especially if perhaps you already know the answer to the question, but you think it needs clarification. You're the perfect person to ask the question or make a comment or whatever. And everyone else will breathe a sigh of relief that you've slowed this person down finally. And a little clarification on the issue. So this works really well, and I would appreciate it if you do. So just raise questions. And I gave a lecture recently in Japan, and I said this, and it was very difficult to get done with the lecture. There were so many questions. It was amazing how many questions. These were 3rd graders. So okay. So where are we in the? So this is the electromagnetic spectrum, and my attitude has always been that we're starting in this region with visible light, where there are lots of applications, lots of sources, very interesting lasers, good optics, perfect optics, near perfect optics, and we're moving to shorter wavelengths, rather than we're starting out here with medical imaging and dental imaging, where it's just making shadow graphs. Not a lot of sophistication in either the source or the optics, more in the application. So we're coming from this direction, where it is sophisticated, and we're trying to bring that into the short wavelength region, and that's been largely successful. And there's lots and lots of applications now. And so we're sort of in this region someplace. The wavelengths are very short, so if you can manage to make optics, you can get very good resolution. And the photon energies that go with this are also very interesting. Essentially, you'll hit all the primary resonances of all of the atoms. Every atom in the periodic chart, you'll hit some aspect of the primary resonances. So if you do, for instance, in imaging, you can do imaging which highlights the carbon edge or the silicon edge or something like that. In fact, we'll mention this application of EUV lithography, printing computer chips, and that's right here at the silicon L edge. So the silicon L edge is about 99 eV, and if you get a little bit below that, there's a combination of materials which happens to make a very good reflection. And as you'll see here in a moment, reflections in this whole region are very, very poor at arbitrary angle or normal incidence. But just around here, there's a terrific combination of materials, and you'll understand that by the end of these lectures. Why does that work so well? But it also points out why these absorption edges are extremely important. In fact, between carbon and oxygen is what's known as the water window. Here, if you image biological materials at a photon energy in here, the photons have enough energy to be absorbed by the carbon to kick out an electron and be absorbed, but not for oxygen. They don't have enough energy. So water, H2O, is relatively transparent. So this is the water window. So I've provided you a few applications, a few important edges. And so these things then sort of fit in what I was just speaking. Just as a practical matter, as we go through the course, we'll see that this is the refractive index, where delta and beta are both quite small. So the optical properties in this wavelength region are quite different than they are, let's say, for visible light. It's very hard to make a refractive lens because there isn't enough of a bending effect. And also, it's a little less than unity rather than a little more. So rather than bend in one direction, you bend in the other. Okay? And this, just for convenience, I will not stop to say it as we go along, but this is F lambda equals C. Just written, frequency is written in terms of omega with an h bar to give it units of electron volts, and the wavelength in nanometers. So the way you read this is that if you wanted to know the wavelength where the photon energy was 100 eV, you divide the 100 eV from both sides, and you get a wavelength of 12.39 nanometers. So that's how you read that. Okay. Oops, don't have to go anywhere. Okay, so same thing here. And also, we often want to flip between watts and photons per second, because in this region, each of the photons has a lot of energy. So there are many applications we're actually interested in photons per second. And this is a conversion. These are the same relationship, it's just that you divide here by time. But these are conversions that we use quite frequently. Oops, can't get used to this. The periodic chart, just the comment I made before, for all of these elements, the primary resonances are in this region, except maybe hydrogen and helium. And then if you allow L edges and M edges, you get the entire chart. So when you're working with X-rays or extreme ultraviolet, you basically are able to cover the periodic chart. So just basic processes now. So this is not meant to be insulting to your intelligence, but just to get the processes right. So for principal quantum numbers, n equals 1, 2, and 3 in the X-ray region, we call those shells of electrons the K, L, and M shell. So if I say it's a K shell absorption, I mean that the photon energy is going to be absorbed by a K shell electron, primary quantum number 1. So in this case here, there's an electron collision induced ionization. So an electron comes in with some energy. It's called the primary electron. Here's the electron. And it knocks an electron out from here. So there's the primary electron is scattered. It comes out at some other angle. And this electron, which is knocked out, comes here. And this photon has to have enough energy to lift an electron from n equals 1 to the continuum. Okay? So that's an electron ionization. Photoionization, same process. In comes a photon, knocks out an electron. This has an energy h bar omega, and the conservation of energy, there's a binding energy to get this electron out of the K shell into the continuum, and so the excess of energy that you have is from conservation of energy, this simple thing. Fluorescent emission is, well, okay, in both processes you now have a vacancy here, and the atom will readjust, and out will come something. And if a photon comes out, we call it fluorescent radiation. So there's the vacancy. Some other electron drops in, and out goes a photon. So that's fluorescent radiation, and it's a characteristic radiation because it's just this amount of energy. Okay? This thing might have had any photon energy coming in. You know, there's an excess energy here that goes into the energy of motion, the kinetic energy, but here it's a fluorescent, very characteristic. And this is the so-called Auger process, where rather than come down and throw out a photon, the electron readjusts by throwing out an electron. And that's called the Auger process. And the electron can drop in from any different level, and the Auger process is an important one. And which of these happens is a bit probabilistic and depends on the charge state of the atom and which levels are involved. Okay. So I'll have something else to say about that. So this is the diagram we were just looking at. And in a very simplified version, all you know about is principal quantum number. So here's your K shell, n equals 1, 2, 3. And so, for example, in this case, you have some photon energy which is more than sufficient to knock out an electron and leave it with some extra energy. So that would be shown here. A photon with this amount of energy, where this is the binding energy, for to go from K equals 1 just into the continuum, requires this amount of energy, and this is the leftover energy, the kinetic energy. So just for process. And so this amount of energy that's just enough to get it out, to take an electron from n equals 1 just to the continuum with no leftover kinetic energy, that's called the absorption edge. So this is one of the purposes of these initial slides, just to get those words straight. That's the absorption edge, and if you have a little, if the photon energy is larger than that, you'll have some leftover energy. Okay? And this is some examples for different charge states on the nucleus. For different numbers of protons in the nucleus, Z, what is the K absorption edge? Okay, so copper is probably one of the more famous ones, right? This is around 9 keV. Okay, there's also the L absorption edge. What does it take to take an electron from n equals 2 into the continuum? So that's the L level. This was K, this was L. Okay, so the L absorption edge, and here are the L absorption edges. And so, for instance, some of the magnetic materials like iron and cobalt, cobalt isn't on here, but let's say iron, has an L edge at 707 eV. So people who are interested in the dynamics of magnetism often use photon energies just above or below 707, 708 eV would be some example of how these are used. Okay, it's a good time for questions. I think this is probably just simple background for everyone, but also, no one's going to ask a question if they don't have a sense of the answer, right? So this is where you can see that you have to ask the question if you kind of know the answer. So please be kind to other people in the room and ask a question.
Can I ask a question?
Yeah, please.
Is there a simple explanation as to why there's roughly an order of magnitude factor of 8, 10, 12 between the K edge and the L edge? So.
You're right. It's roughly an order of magnitude here between the two. And why is that? We'd probably start with probably should go back to the Bohr model, right, or something like that, and see what would be the answer there. Just look at that little equation.
Yeah, it's like the n squared thing.
Yeah, right, probably. Okay. So we know there's a little bit more sophisticated model of the atom. So here we are with the various quantum numbers, and again the letters K, L, M for the shells, and principal quantum numbers n equals 1, 2, 3. But then there's the various angular momenta, and this causes a breaking, shifting of the energy levels, not for the K shell, but for the L shell and the M shells. And now you get into additional nomenclature. For instance, here for the L shell, you have L1, L2, and L3 absorption edges. So you'll see that and hear that. It may be in some of the slides, so now you'll know what it means. And this is for copper, Z equals 29, and I put the numbers in here. And so you can see what are the, for instance, the K absorption edge for carbon, for copper here, as we saw before. And these are the emission lines, the natural emission lines. And then these are the various L edges and the M edges. So how much energy is required? And again, you can see there's a sort of an order of magnitude difference there. Okay. And this is an example this is just a table of these various binding energies in electron volts for many of the elements. And if you go to this website, you'll find all of these things, and you'll find many, many other things. So if you're working in the X-ray region, you've probably discovered this website because it has just tons of information. This is put together by Eric Gullikson. It was originally by Burton Henke, but Gullikson has been doing it for almost 20 years. And they're quite useful. It gets in excess of 1 million hits a year, individual hits of people who are active in the field using it. This was this business about when the atom readjusts, does it throw out a photon or an electron, the Auger process? And this is showing as a function of Z, what's more likely to happen? Is it going to be a fluorescent emission? So looking at the K shell for low Z, small elements, it's showing that the fluorescent yield is not very good, but it's becoming very strong for high Z. And that's because these are beginning, when you get to the higher Z, the K shells are quite isolated, and they're quite likely to emit a fluorescent photon. Whereas in the low Z, all of these electrons are very close to each other, and they perturb each other. And that's what leads in the end to whether you would have an Auger process or not. And this I just put in there. It doesn't quite fit here, but if you had a process where you send in a photon, let's say, and it gets absorbed, and out comes an electron, and it's in a solid. It's not an isolated atom, but it's in some solid. How far does it go? And it's an important aspect of many of the applications we get involved in, that the electron doesn't go very far in a solid. And it almost doesn't matter what is the solid. And this is showing curves of mean free path in nanometers. And you notice the scale, it's only a few nanometers, versus the photon energies, which the electron energy, which can be in a very, very wide range. So at very low energy, there aren't, it's interacting with collective processes, and absorption is not very efficient. But over a very wide range, from 10 to 1,000 or a few thousand eV, the electron range is quite short, and it's almost the same for aluminum and gold. And in fact, this is a universal curve for all different elements. So you can see again that the electron only goes about a nanometer, so half a dozen atoms for energies, electron energies are from 10 to 1,000 or even a few thousand. So, for instance, people who are involved in surface science or something, where you send a photon into the material can be quite thick. The X-rays may be absorbed in microns of distance, but the electrons that get out, for them to see the properties of the surface, they're only coming from the outer few nanometers. Okay? So this would be an example where this matters. Another, what's the scale of the electron orbitals in atoms? So this is argon, I believe. Yeah. So this is an argon atom, normalized radius, where A0 is from the Bohr atom, the first Bohr radius. And this is showing where the electron charge is. So as you go from a low Z, like hydrogen of the Bohr atom, to higher and higher Z, you might think that the atoms are getting bigger and bigger. The electron distribution, the cloud of electrons around the atom, is getting very large. It's not really the case. What's happening is that the higher charge on the nucleus is pulling the electrons in closer. And so most of the electron charge is being pulled in. There is some of the outer electrons that now go out quite a bit further. But if you look in a solid as to what's the separation, what's the between atoms, planes in a crystal, for instance, you find out it's quite a small number. It's just a few Bohr radii. One of the reasons that this comes in is when you're doing calculations of these electromagnetic calculations, you're starting with Maxwell's equations, and you're doing things, and you make certain assumptions about the wavelength and the charge distribution on the particles. And if you're working at the longer wavelength, X-ray wavelengths, soft X-rays and EUV, where the wavelengths are of order a nanometer, the wavelength is much larger than the atom, and you can make the assumption, you can make some assumptions that make the mathematics quite simple. So for soft X-rays and EUV, it works out quite nicely to say that lambda is larger, and all of the electrons are acting the same. They're all seeing the same phase. So they're all oscillating together. There's what's called n-squared effects, which we'll speak about later, and that is the radiated fields are all, from every electron, are all adding in phase because they're all so close together that they see the same incident phase. Whereas when you get to real X-rays or hard X-rays, where the wavelengths are down around an angstrom, 1/10 of a nanometer, well, that's not the case anymore. You have an atom, it has a charge distribution, and when the radiation comes in, different electron positions see a different phase, and as you look off at different angles, you get different scattering effects. So there's a strong angular effect. And in fact, when I was writing the book, the reason it says soft X-rays is just because of this. Okay, it was easy. You'll see that where it comes up in the what's the scattering cross section for an atom. You can make two approximations where everything becomes simple. One is going in the forward direction, and one is if the wavelength is larger than the atom size. So that's where that comes in. So that's why I put this here. Also, when an electron drops from an upper level into a lower level and throws out a photon, as I showed in the previous thing, it's not quite that simple, right? The atom is undergoing a change from an upper level to a lower level, and there's wonderful books you can read about this. I like the one by Luden. But at any rate, what's happening is there's an oscillation of the charge distribution between these two states, and what's really happening is not that a photon just got thrown out. What was the bandwidth associated with that throwing out or emitting the photon? And it has to do with the lifetime of the states and the oscillation between the upper level and the lower level, and gradually the atom goes from one state to the other. Okay? So that comes in when you're looking into laser effects in particular. Okay, this is simple stuff, but important. And that is, what is the incremental absorption of X-rays as the X-rays go through some material? So if you start with an intensity I sub 0 at some photon wavelength, and you go through a thickness of material, it's shown as structured, but it's just meant to be a thickness, and the material has a density rho. So if I use rho, it's in, let's say, grams per centimeter cubed or something like that. It's a mass density. What's the intensity coming out? This is what it started at. This is what it is after some propagation distance x, and you can show that the ratio is an exponential rho mu x, where mu is just a coefficient that fits these exponentials. So that if this is grams per centimeter cubed, and this is, let's say, in centimeters, then this combination is grams per centimeter squared, so this is the opposite. And it's just that. It's just a coefficient. And this is showing an example, again, for a copper foil as a function of photon energy. And this is the value of mu going along. These are in these units, this is what the number is. And it's dropping off until you come to that magic 8.9 energy. So this is where the photon energy is just enough to kick out not only an L shell, but a K shell also. And so there's an increase in the absorption. Okay? And that's how you calculate it. And if you plot Ix versus I0, it'll have this exponential decay. And that's in terms of a mass density, but you might also be interested in doing it in terms of an atomic density. So I use lowercase n with some subscript to mean density. Atoms per cubic centimeter or electrons per cubic centimeter, etc. And that's how we relate these two. And now the cross-section will look the same, but the units are changed now. So these are megabarns. Barns is, I think, 10 to the minus 24 centimeters squared. So this is megabarns per atom. And this is from Ingolf Lindau and his student, who probably did all of the work, and I unfortunately don't remember his name. But anyway, they have it done nicely depending on what the initial state was. So this relationship becomes this relationship. Okay, so here I was showing you what one of these curves would look like. But now to be more specific, and this is coming from the website I told you about before, you can do, if this looks strange to you, you can get there in various ways. So again, in these units, this is for carbon, and here is what the curve looks like. Okay, and I'm going to show you some other curves in a moment. I'm going to choose these silicon and molybdenum because they form the combination of this multi-layer pair that works so well below the L edge. But anyway, so you can see how that goes. And so here's the K edge of carbon shown here. Okay, that would be right here. And a couple of these, by the way, are in the back of the book. I picked out a number of elements so that if the purpose was if you were working on an airplane, or you didn't have access to a computer, so you were working on an airplane, let's say, and this was a few years ago, you would have something there that you could do some homework problems. So there's quite a few chosen there for just that reason, and they're done in both of those units. So here's the curve for silicon, and probably molybdenum is going to come next. And now here's the K edge, right, for silicon, just below 2 kilovolts, something like 1.8. Here's the L edge. There's a very dramatic effect here at the L edge. So just below 100 EV, there's quite a drop in the absorption cross-section. Okay. So this is getting near the end of this chapter 1. And this is about scattering, diffraction, and refraction. How do we use these words? Okay, you hear them used sometimes interchangeably. Sometimes you see people who obviously must know better, and they use the words in a jumbled way, and the units that go with them are also sometimes jumbled. But I think in my book they're correct. And this is just a small summary of this whole thing. So if you have radiation coming upon, so it's shown here as a nice plane wave illumination coming in at some wavelength lambda, so nice phase fronts here propagating in, and the dot is representing an atom. And so let's say a single electron to start with. So the single electron is there, in comes the radiation. It's going in the K direction, the forward direction. It has an electric field up and a magnetic field to the side. And the electric field is the dominant force. The magnetic force is quite a bit smaller. And you can see that in the book if you really get into that. But anyway, it's the electric field that's dominant in this Lorentz force. And it makes the electron oscillate up and down. And whenever a charge is oscillating, which it is, it radiates. Okay? And if it's just a free electron, then the emission is the same in all directions. Okay, in the plane. So in the plane of where the electric field is going up and down, in the horizontal plane, the angular distribution is completely uniform. Okay, so that we call scattering. It takes something and it sends it in a different direction. That's how we use the word scattering. That's what it means. Something was coming this way and it's gotten sent out. So it could be some rough object that you shine light on and the light gets spread out all over the place. That we would call scattering. If it turns out that you didn't have one electron but you had several electrons, could be an atom now, right, in a relatively short wavelength, because if the wavelength is comparable to the size of the distribution of charge, now you have this effect where this electron is seeing one phase and this is seeing a different phase, and off at an angle everything looks different, and so now you're going to get some angular distribution to the scattering process. It's still scattering, we still use the same word, but it's not isotropic anymore. It's highly anisotropic. Okay, so in the hard X-ray region, if you're looking at scattering, this is what you'd see. Okay, if we have a crystal, we use the word diffraction. Okay, but there's this is where there's a transition of both words here. Each of these different atoms is scattering the radiation, and if it wasn't for all their neighbors, the radiation would go like this in all directions. But if you have a very well-defined periodic pattern, there'll be a cancellation of, you have these random angles, But there'll be cancellations in every direction except some special directions where everything adds up in phase. At the other angles, they don't add up, and this is a good thing to talk about, maybe at a coffee break, or we have a free lecture, the fourth lecture. But at any rate, in a certain direction, they all add up in phase, and that's where we make the transition from referring to the individual scatterings adding up to a diffraction pattern. So a diffraction has the sense of an orderly process to it. Okay? Another case of diffraction is when you have radiation incident on some small opening, a pinhole, and this radiation comes out, and depending on the size of the pinhole, there are boundary effects. The radiation will be in a forward lobe with little side lobes and everything else, but there's a very predictable pattern to this. It's not just arbitrarily scattered in all directions. Of course, there is scattering by the atoms near the edges where they're interacting with the incident radiation, but altogether those scatterings are able to build up a particular nicely defined diffraction pattern. So that's the use of the words. Refraction is just the bending at an interface. So like in a lens, the different angles are bent in different ways to form an image. I got way off there. Yeah, so that's refraction. And then total external reflection is a special topic for X-rays. Because in general, for X-rays incident at some angle on a surface, as you'll see later, the reflection coefficient, how much light is reflected, for instance, at normal incidence, the reflection is so incredibly small at X-ray wavelengths, it's essentially zero. You'll have a relationship for this in one of these lectures, but at any rate, it's quite small. But if you come in at glancing incidence, there's a very good reflection. So again, if you come in here, it's almost zero. If you come in very close, within a few degrees of the surface, depends on the wavelength, photon energy, but if you come very close to the surface, you can have a very good reflection, 80-90%. And so it's a common tool. We use it in the laboratory all of the time. And so that we're going to look at that in one of these lectures. Okay. So any comments in general? Okay, so diffraction. So we're going to, in the next lecture, we're going to speak, well, there'll be a couple of places where we speak about this a little bit more. But for instance, even from high school, you probably did this, where you have a diffraction grating, you have some planar light coming in at some wavelength, okay? Could be X-rays, could be visible light. And if you look at, so there'll be a certain amount of radiation that goes straight through, okay? But there's a certain amount that will be absorbed, or partially absorbed. But there'll be some radiation off at different angles that just add up in phase, so that all of these different openings, the radiation coming out, all add up in phase. And those are called the diffraction orders. And there's a relationship between the sine of this angle, the wavelength, and the period, middle of one to the middle of the other, let's say. Okay, and this is that relationship. And m equals 0 means the forward direction, and plus or minus 1 means it could go up or down. And then depending on whether this is symmetric or asymmetric, you may get second orders, or you may not, but you'll certainly get third orders. So this is a diffraction that you're used to, but it's very commonly used in the X-ray region. This is, refraction, absorption is so dominant, and refraction is so small, you don't have that many tricks. So you have glancing incidents you can use to get radiation from one place to another, but diffraction is another one of those examples. And in fact, I'm going to show you a zone plate that's used for focusing or imaging in a moment, and the way to understand it is to remember this relationship. So when I show you the zone plate in a moment, the circular diffraction pattern, I'm probably not going to show you the forward part. We know it's there. And rather than show you both the plus order and the minus order, I'm going to show you one or the other. Okay. And by the way, what's the percentages? So the amount of, if this is a completely opaque, so some X-ray energy, soft X-rays or EUV, this is a gold, and this is opaque to these energies. So there's an opening, here, the first orders will each have about 10% of radiation being diffracted. So when we talk in a moment about a circular diffraction grating, a Fresnel zone plate lens, it'll have about a 10% efficiency. At best, actually, it'd be probably a little bit less than that. And that sounds like, gee, why would you want to use it? And the answer is because you can get very high resolution focusing or imaging, and you can't get it in any other way, at least at this point. And now reflections, I told you that reflections off some surface, any surface, were going to be quite small. As you'll see in one of the lectures, remember that the refractive index was 1 minus delta minus plus I beta, where delta and beta were both very small, and they're wavelength dependent. In fact, they depend on the wavelength squared. So when you get into hard X-rays, delta and beta will be really small numbers, like 10 to the minus 4 or something like that. So when you square them, you'll see that. So for normal incidence reflection off a single surface, some material with a single surface, the reflection coefficient is delta squared plus beta squared. So it can be like 10 to the minus 8 for X-rays. So really quite small. Longer wavelengths, it's a lambda squared effect, so these will become larger. But even in the EUV, it's also quite small. 1 part in 100 or 1 part in 1,000, quite common. For delta alone, and you square it. But if you have a lot of surfaces, you make what's called a multi-layer coating, and you get a positive reinforcement, a coherent interference effect, then you can have radiation coming in, and although any one surface might have a very small reflection, for every pair you've got 2 interfaces. And so you run through these, you propagate in. You can't propagate very far, although there's some subtleties here. But as the radiation propagates in, it scatters off each of these things. And if it's just the right angle, which you'll see in a moment turns out to be the Bragg angle, just like in a crystal, just at the Bragg angle, these electric fields are all adding up in phase. And the intensity of the reflection goes as the electric field squared. So if you can have a situation where you propagate in and you get 30 different, let's say you have 20 layers, that gives you 40 interfaces, and the electric field goes as the square of that. So you can see where you can pick up a factor of 1,000 or so, and this reflection coefficient, which might have been very small for one interface, can become very large. And for instance, I mentioned this extreme ultraviolet lithography. Hopefully the way to print computer chips in just a few years from now is completely dependent on that effect, with moly and silicon, molybdenum and silicon. The other thing is then, just to go with the diagram first, so if you can have you could form an image with some reflective optics. So this has to be close to glancing incidence, so this angle can be quite small. But if you have some situation where you have light coming from here and you're back illuminating this, you'll form an image over here. And so what you have is 2 reflections, each with a slight curvature to it. So the slight curvature on this one provides an imaging capability in one plane, and the slight curvature on this one can't be too much because the angle is only a few degrees, gives some focusing in the other direction. So you can form a 2-dimensional image with 2 of these things. And this was introduced by Kirkpatrick and Baez many years ago, Paul Kirkpatrick and Al Baez. And this is called a KB optic, and you just see them everywhere. And perhaps everyone likes a little side story. So Paul Kirkpatrick was the professor at Stanford, and Al Baez had been a professor himself at a smaller school, but didn't have a PhD in those days. This was probably in the 1940s or something, going into 1940s. And so his name was Al Baez, not Baez. But so he was the student of Kirkpatrick at Stanford, and later, and he had a daughter, Joan, Al did, who became a very famous protest guitarist, actually a great singer, really. If you've heard some of her operetics, she's a really, really talented person, But at any rate, she became very famous, and they changed her name to Baez. So she became Joan Baez, the folk singer. And Al, everyone called him Baez, and he said, he just said, I just gave up after a while. So here are some, I'm sorry.
I'd add something to that.
Oh, please.
Because I met Al Baez a few years, many years back now, but as an addendum to that story, he always used to get asked at conferences, are you related to the famous folk singer?
Yeah.
And once, apparently, somebody asked Joan, are you related to the famous physicist?
No kidding, wow. That's a good story.
I thought that was brilliant.
Yeah.
I'll add one more thing. We have a lecture series from the Institute of Physics in Ireland every year for schools. And Al Baez did it maybe 15 or 18 years ago here in the Royal Dublin Society, where he talked about holography.
Oh, yeah.
So he's been here.
Oh, yeah.
Right. So some of us met him, maybe Paul at that time. Maybe he was too young. He was probably a child. He gave fantastic lecture on holography in Dublin, in the Royal Dublin Society.
He's a guy who really understood all this, right? Yeah.
Yeah.
His contribution was really very important.
Yeah.
He's well known because of this optical system, but also he published the first paper on Fresnel zone plates. It's even much more important for
Yeah, and he was going to use them in some orbits, and then maybe. We had a conference in 1980, and on kind of all of these same things, and Al couldn't make it. It turned out he was organizing a UNESCO meeting at the same time, Al Baez, but Paul came, and Paul at the time was 90 years old, and so we weren't quite sure what was his mental facility at the time, is his Alzheimer's setting in or whatever. And so I called him on the phone, and I asked him if he'd come, and he said, wait a second, I have to ask my wife, hey May, can I come to this meeting, and everything. So he came, and there's a couple of interesting things about the presentation. First of all, he was perfectly lucid. I mean, this guy hadn't lost anything. And an example of this was he had many students who did X-ray holography and imaging of all different kinds, and many of them were in the audience. They were all also of retirement age by this time, but they were all sitting there. And somebody asked Paul, who was your best student? And just like that, he said, oh, that's easy. It was Joni. I taught her to play the guitar. So this is just some of the things about the short wavelength regime. The optics really do behave differently to some extent. The index of refraction is very close to unity, slightly less than unity, very important absorption, so absorption plays a major role. Light or waves bend away from the normal at an interface because of this minus sign. Where does that come from? That raises several questions in your mind, and you'll have another chance to ask about them. Absorption is significant for all materials at all wavelengths. Because of absorption, refractive lenses do not work, nor prism except, you'll see someplace else, except if you get up to 20 or 30 kilovolts, then you can make these compound refractive lenses, so-called Sniggerov lenses. So in general, refraction simply doesn't work because of absorption. But if you get to high enough photon energies, remember the absorption curves were diving. Actually, they go off at a high order of the photon energy. So it becomes... And then there's this glancing incidence reflection, which we talked about. So these are the available methods that we use. Glancing incidence reflection, multi-layer interference coatings, diffraction. So here is our circular grating, which we'll come back to later, where it's clearly circular, but the period is getting smaller as you go to the outside. So the light coming in the outer region sees a small period here, so the diffraction angle is larger. In the inner regions, the period is quite long, so the diffraction angle is quite small, and they can be arranged so that the radiation from the whole area will all come to one place as a focus or as an imaging tool. Okay? And it's just because you have to set the radii to match that. And then here's the diffraction and the pinhole. This is refraction which would work for harder X-rays, notice that it's the opposite shape that you would think about. So this is where X-rays are really different. And this is the compound refractive lens of Snegerev and Langelier and others. Some comments? Yeah, good. Thanks.
Can I ask what's the material for the grating or the coating material?
Yeah, you mean like what did I do?
Because I was.
You mean like here?
Yeah.
Yeah,
because I was worried the wavelength of the X-ray, soft X-ray is really short, and could it be, what do you say, diffracted or scattered by the atom structures?
In fact, I mean, that's what's happening. We don't look at it in that detail because we've come to understand that diffraction comes from scattering by the edges, right? That's where the interaction is. But they all add up in a certain way in phase, and they make a diffraction pattern. But to go back to your question about what are the materials here. So for instance, in these zone plate lenses, which is just a circular version of this, okay, the common materials are gold and nickel, and other materials also. The nickel at certain wavelengths, nickel's absorption edge is, I forget where, it was on that chart probably, but around 700 or 800 eV. But you can get little phase effects. Depending on if you use gold at the soft X-ray wavelengths, then this will be totally opaque. And that's where you get the 10% efficiency into either order. But depending on the photon energy and the material, if you use nickel and you work just below the nickel edge so it's not quite so absorbing, you can get a phase effect. And you'll get not 100% absorption, but a little bit of a phase reversal as it goes through. So you have to make the thickness right. And you can increase the diffraction efficiency above the 10%. And in fact, in the X-ray region, so harder photon energies, you get into a different problem, but you can make structures which are just phase effect structures, where absorption plays some role, but the phase effect is much more important. So I have a colleague who is working now on making zone plates for 25 to 30 keV, and the efficiencies are going to be much higher, like 30%. In fact, has made them and used them in some experiments, some focusing experiments. So depending. So yeah, so you're on. Those are good questions. Thank you. That brought up some additional points. And what else? And so also here, we'll see some examples here. In order to make this work very well, you want to choose these materials just very carefully. And also, I said you would propagate in a certain distance. I said there's a little subtlety there. You know, if you look at the crystal from one of the earlier patterns, but here, if you look here, if you can produce a strong diffracted wave, it interferes with the incoming wave. So there's a wave going in and there's another wave coming out, and they interfere with each other and they produce an intensity distribution in the material. And in the crystal it's extremely important. But when you tune around the Bragg edge, around the Bragg angle, when you think you're just about there, what's actually happening is you're playing with this interference pattern, and you're doing it in a way that the maximum of intensities is in the low Z material. So for instance, in a crystal, it's much more important. There's what's called the Borman effect. It's an old effect, and what Borman observed was if he had a thin crystal, and he put his radiation in, and he played right around the Bragg angle, radiation, when he hit the Bragg angle, not only would he get a good reflection, but he'd get a good transmission also. And what's happening there is a really interesting effect, that the interference pattern is such that the high intensity is right in the middle of the planes, not right on the atoms. It's right in the middle, and just at the plane of the atoms, where this is X-rays now, the K edge would do the absorption. But the K edge, remember, it was very compressed. Those electrons for higher Z materials were quite compressed. So you think of these crystal planes, but the atoms are there, and between planes there's all of the valence electrons interacting. That's where you put the high intensity. So you still get the scattering for the crystal diffraction from the valence electrons, but the absorptive part, where the atoms are, where the K shells, electrons are, there's no intensity. And that's why crystals at 25 or 30 kilovolts, if you had near parallel X-rays, for instance in the synchrotrons, they can get like 99% reflection from a crystal. And it's this interference effect which is really playing an important role. Good. Okay, so in the next lecture we're going to use Maxwell's equations, and we're going to look at scattering processes, and we're going to see, for instance, for a single free electron, radiation coming in, as I mentioned before. So here's a single electron. Our radiation is coming in this direction, electric field in this direction, magnetic field here. And the electron is made to oscillate up and down. Okay? And there's a radiation, what they call a donut pattern. And it's scattering in the plane. It's uniform in all directions for the free electron. And off-axis, it has a sine-squared behavior. And we're going to go through some mathematics. And of course, you can't use mathematics in a lecture like this because you can't keep up with it, right? So that's why we have the handout, so you can just write little notes on it. But it's mainly to guide you through what's the thinking on it. And if you want, you'll go back and look at it later. But the equations that we'll wind up learning is, what is the power per unit solid angle of the scattering process, so this sine squared. So this, you would have learned this in some electromagnetics class that had nothing to do with X-rays, perhaps even in undergraduate class. You would do what's called dipole scattering, and you'll find that the cross-section for an electron, what's the equivalent area that it presents to the incoming radiation to scatter it, has this, it's called the Thomson scattering for a single electron. And this is the formula, and this is the classical electron radius squared. It's a definition. And it's about the size that you could associate with that. And then we'll look at a bound electron. Suppose you had only one electron, but it was bound to a nucleus. Okay? The scattering process would be the same, but if there was some resonances, some atomic structure, energy levels, and let's say put H bars on all of these things, and you'll see that for a bound electron, there's a significant enhancement of the scattering cross-section right at the resonance. So this is not unusual. If you have some resonance structure and you excite it, if you get near the resonance, you're going to get a really large effect. So we don't have a problem in our cars anymore, but years ago, your cars were not adjusted so well, and if depending on how the carburetor was set, if you let your car idle at a traffic light too slowly, you'd get to the resonance, the mechanical resonance of your engine, and your whole car would start shaking. So it doesn't happen anymore. But it's just that there is a resonance. It's such a massive structure. It's a very low frequency resonance. For bound electrons, the resonances are quite high. But if you hit the resonance, you will really hit the money here on the cross-section. Okay? So we're going to talk about that. And these are for free electron lasers. And notice on this one, for the free electron single free electron laser, single free electron, there's no wavelength dependence. So it's the same cross-section for microwaves, visible light, and X-rays. When you start to introduce resonances, well, that story changes. And then there's the question about, well, these were free electron, a single bound electron. What if you have a lot of electrons? It's an atom. It's an argon atom, and you're illuminating it with some photon energy, h bar omega. And now you'll find that the cross-section is increased by some factor. Okay? And that depends on all of the electrons that you have and all of the resonances. Okay? So this is a sort of a classical view of it, semi-classical, but so we're going to do that again later and show you what the result would be with quantum mechanics and that. So this will be the next lecture, which is mostly out of chapter 2.
What did gamma represent there?
I didn't. Oh, so gamma. So quantum mechanically, it would be a lifetime effect, but it could be an absorption effect. You get either way. It's something that limits the bandwidth. So if this is very small band.
Atomic parameter or field parameter? It characterizes the atom or the field?
So for the proper quantum mechanical, this is from the atom. This is the lifetime between these two states. The omega s is representing the level between n equals, maybe n equals 2 and n equals 3 and some j values. And there's some lifetime. So remember the oscillation that goes on. So that gamma is a measure of the lifetime. How many cycles? What is the bandwidth as a result? But in a classical picture, it would just be an absorption effect. So we will start with Maxwell's equations, and from Maxwell's equations we'll get the wave equation, and from the wave equation we'll do scattering and refractive effects. And at least in our university, and I think throughout the United States, we have PhD oral exams. And very common, usually in our school the students get to choose 3 topics. So often in the PhD program I'm associated with, they choose quantum mechanics, solid state, and optics and electromagnetics. Maybe here you would choose plasma physics as one of the topics instead. But they do, and this is often, not always, it's often one of the topics just to get the students started so that they can relax and say something very knowledgeable. How do you go from first write Maxwell's equations and then show us how you go from Maxwell's equations to the wave equation, and then simplify it and solve some problem. So it's quite a common thing for us. And what we'll see here now, so in this chapter 2 we'll be talking about the scattering process. What happens with an isolated electron, free or bound, or an atom. So those are the kind of things we'll solve. But in chapter 3, so the third lecture, we'll be looking more at what about when you have a lot of atoms all together. Here they're purposely shown to be amorphous, not a crystal, but in both cases with some refractive index. What's the properties of reflection, etc., etc. So we'll look at that. And this is just a little bit more of, this is why I want to have an overview, so that rather than just start solving problems, you see what's the difference. So in the one case, Maxwell's equation is to wave equation, but now what do you do with it? If there's an isolated electron or an atom, we call it a scattering process, and that's what's shown here. So we'll define what is a scattering cross-section, what is the Thomson scattering for a single electron, free electron. What if it's a bound electron? We call it Rayleigh scattering. I'll show you a slide and say something about the color of the sky and the sunsets and stuff like that. And the atomic scattering factors, which are really important. And you don't calculate them, you measure them. Okay? And then, so that was individual scattering centers. What about if you have a whole bunch of them? Now you get into, here you didn't have refractive index. Now you have a refractive index associated with many atoms. There's a special role for forward scattering. A lot of things simplify, and you'll see why. And then, and what's the role of the bound electrons? And how did you get a refractive index which was a little bit less than unity? If the refractive index is a little bit less than unity, what does that say about the phase velocity of the wave? Remember the phase velocity for visible light is c over n. And n was like 1.5 for glass or something. So you know that when the light entered into the glass, it slowed down. Now we have X-rays, and c is 1 minus delta. It's only a small effect, but it suggests that the phase velocity of the wave is faster than the speed of light. What does that mean? Is this giving Einstein great concern or not? So that's, when we come to it, we can talk about it some more. And so the refractive index, we'll see that we will have learned here about these atomic scattering factors. If you had an atom, it scatters, it has a lot of electrons. It has a cross-section, it has a cross-section for scattering, which is modified depending on how many electrons, what's the photon energy, how does it compare to these resonances. And it's a very complicated factor, and it's a complex factor. And it has a real and imaginary parts, and one is related to delta and one to beta, and we'll show where those relationships come from and how do you get them. And then we'll go into these things about, external reflection, reflectivity versus angle, Brewster's angle. Brewster's angle is a real effect. And Brewster's angle is the angle, depending on the polarization that you enter with. If you come to a surface, Brewster's angle is an angle where there's no reflection. So if you've ever seen a rod on a laser, the rod will be so long, maybe a neodymium YAG is an example I'm thinking about, but others also. The rods are cut at a certain angle, and that's for a certain polarization will have no reflection at the ends of the rods. And it's also good, it sets the polarization of the laser. And so for X-rays, that it's called Brewster's angle. He was the one Scotsman who observed this and described it first. But for X-rays, Brewster's angle is very close to 45 degrees within delta, so a very small amount. So if you come in with a certain polarization on a surface just at 45 degrees, nothing comes out. And we have, without meaning to, we have demonstrated this. Because we designed a synchrotron beamline with some mirror that went off, and we weren't thinking. And so we had the horizontal polarization of the synchrotron radiation hitting a mirror, which we thought was going to another station. Zero. Okay, so those are the kind of things we'll talk about. This is the scattering business. This is what the scattering cross-section is about. This doesn't have to do with X-rays or even with just radiation. Just any object. If you have radiation coming in, and there's a likelihood that whatever's coming in is going to be sent off to different angles, you can define a cross-section for scattering. What is the likelihood that this incoming something or other will hit something and be sent off in a different direction? So an easy place to get started is this game of billiards, right? You have these balls, and you hit with the stick another ball that's going to go, and you hope it's going to hit one of the balls and direct it in some certain way. And so if you want, there's a scattering cross-section there, you know. If you come, in that case it's a very simple one. It's just the geometrical projection of the area. It's just a circle. That is the cross-section. It's really well defined. You get within the cross-section, you get a scattering. If you're outside of that, you don't get it. Okay, well, you can imagine with charged particles, incident on charged particles, you get something quite where you get angles all over the place depending on how close you come. So that's bremsstrahlung, right, in the plasma, for example. But at any rate, so the way of defining this scattering cross-section is that it's the total amount of power scattered. This bar means it's an average, a time average. But you're integrating, if you're looking at the power here going to all directions, that's the power scattered, and this is the Poynting vector. This is E cross H, the incident power per unit area. So this is power per unit area coming in, and the total power being directed in all over the place. So this is watts, and this is watts per unit area. So you flip it, and you get a cross-section in area, okay? Maybe centimeters squared. Some questions you would ask, is it isotropic, same in all directions, or anisotropic? So again, if the wavelength was long, and it was an atom and the wavelength was long, it'd be isotropic. But if it was an atom and the wavelength was comparable, as shown here, then it would be anisotropic. And is there an energy or wavelength dependence in this cross-section? Now we're into X-ray related things. And for the free electron, we get the Thomson cross-section. The bound electron actually has a strong dependence on the binding energies of the electrons. What's the electron energy levels? And the multi-electron atom turns out to have this atomic scattering factor squared. The atomic scattering factor is a measure of what is the electric field, not the intensity, but the electric field at some angle compared to what it was for a single free electron. That's the comparison. And so, because it's electric field, it gets squared. And so there can be some interesting effects there. So that's how we define cross-sections, and what we'll do in the next lecture or two, I keep pressing the wrong button, is we'll develop these relationships. And again, So these are atomic scattering factors, in this case for silicon, Z equals 14. This is the thing that you've seen before, the mu zero. This had to do with absorption. I told you when you calculate scattering factors, there'll be a real and an imaginary part. It's a complex quantity. The lossy part, I call F2, is related to this. They should look the same. The scales are different. But the imaginary part of the scattering factor is just one-to-one relationship with mu, the absorption cross-section. But this is the real part. This is related to delta. Okay? And it's interesting, if you get to high enough photon energy, this becomes Z. So this would be 14. So if the photon energy is way above all of the absorption edges of all the binding energies of the various electrons, then the real part of the scattering factor asymptotes to Z. So at lower energies you'll have all of this structure. But so for molybdenum, we'll see in a moment, Z equals 42. This will eventually level off to 42. Okay. And what else should I tell you? So you can see the rich structure here now at the K edge and the L edge. And I was telling you that this moly-silicon is a very interesting multilayer. It stands out amongst all others at all photon energies. And it is the reason that this lithography will be done at 13.4 or 13.5 nanometers, because that corresponds to a photon energy just down here someplace. And also the absorption part is dropping off here as energy cubed. This is why when you get out to, say, 30 keV, so this is 10 keV, 30 keV, you can do a refractive lens, just because this absorptive part is dropping so quickly. Yeah?
How can we determine the atomic scattering factor?
So the question is, how do we determine the atomic scattering factor?
Yeah.
So we're going to talk about this in the third lecture, but basically we measure the absorptive part. This, we could measure this with foils, right?
Yeah.
And thin foils. And if we know mu, there's a simple mathematical relationship between mu and F2. So we can get F2. We can measure this part, and it's done. And that's what's on these this website that I told you about. And the question is, but how do you get this part? So in principle, you can measure it. You can make interferometers and other things, but it's not what you actually do. What you do is you use Kramers-Kronig mathematical relationships between F1 and F2. So we'll come back and I'll answer this more completely, and I'll show you how they actually do it. What are the relationships? And it's at the very end of chapter 3. There's a little section there on that. So basically, we measure one, and then we use the knowledge of that over the full spectrum to calculate it at every point. You could actually measure it, and there have been some measurements. And when we get there, I remember I added some references just so you could look them up. How would you do interferometry? How would you do modeling of reflections off a surface in order to get this thing? But it's a great question. Great, thank you. Okay. So we should be coming to an end here soon. But so then we will get to this. This is from the front page of chapter 3. But we'll be able to do these kinds of problems. We'll see what the refractive index is. We'll have some mathematical relationships for what these are, but they depend. It's simple for hydrogen, but we can calculate it. But when you get to aluminum or copper or something, there are too many electrons. It's just too complicated. So we measure it as we said. But so we'll have this. But this is, and you notice it has this wavelength squared in here and the atomic density. But this is way too complicated to carry around in our heads, so we abbreviate it in this. So this is just a shorthand abbreviation, okay? And there's a reason why this should be a plus sign. In many cases, in the older literature, meaning only 10 years ago, you'll see it with a minus sign. But I think I've pretty much convinced everybody that they should be using a plus sign. They just have to change their computers. And this goes back to Compton. Compton scattering and all kinds of things with Carl Compton, a Nobel laureate. And he wrote the expressions. For instance, I think he was among the first to do total external reflection, but he certainly was the first to give such a wonderful explanation of it. But basically he wrote a wave. It depends on how you represent the wave mathematically. So I will always write it as e to the minus I, and then in parentheses omega t minus k dot r. And he wrote it as plus k dot r. If you wrote it the way I do, it suggests that you have a wave that's propagating to the right. It's propagating in a positive direction. But electrical engineers will write it the other way. And he wrote it in that manner. And if you wrote it as e to the not minus I, electrical engineers would write e to the j omega t plus kr. And if you did that, then for absorption, you'd have to have a minus sign here. Otherwise, you get X-rays going into a material and they grow in amplitude. That's not good, right? So if you write e to the minus I omega t, you have to have a plus sign here to have absorption giving a decaying wave. And if you wrote e to the plus j, as Compton did, then this should be a minus sign. Okay, so there's quite a few formulas here.
David?
Yes?
I've got minus in my presentation. Do you want me to change it?
Absolutely. I'm getting everybody to change, right? In fact, you know...
Not minus too.
Engineers.
There's one other thing, you know. We will, many of us speak about the brightness of radiation or the brilliance of radiation.
It is radiance.
Huh? What?
It is not brightness. It is not brightness. It is not brightness. It is radiance. That's what
yes.
concern.
You're correct. You are MKS correct. Right. But anyway, it's older people, they learn. In optics, we say in a perfect optical system, brightness is conserved, and we have some meaning to that. And we don't say brilliance is conserved. In fact, we say the older you get, the less brilliant you are. Only the graduate students are brilliant, you know. So I've been trying to convince everyone that they should use brightness. And I noticed that Claudio Pellegrini, one of the originators of the free electron laser, recently wrote a history of free electron lasers. It's a wonderful article. It just appeared recently. And I noticed that he had switched over to brightness. So, okay, anyway, we're going to calculate this. For total external reflection, this is the angle that you have to be within at the surface. And we're going to calculate that. And it turns out to be incredibly simple to do. And we'll do all of these other things. This is the Brewster angle at 45 degrees. So, see if I can wrap this up. So these things we've seen now, okay? This was the refractive index we're going to get, and it depends on these real and imaginary parts of the atomic scattering factors, which look like this. This we're going to calculate. We're going to start with Snell's law, which we should all know, and it's just an electromagnetic phenomenon. And we'll show, if for those who want, it's written out line by line in the book. We'll just outline it. But we'll show, and we'll go through this graph more slowly and show you that, in fact, this is the critical angle. So depending on the value of delta, so this says for gold at 1 kilovolt, delta has this value, and you can calculate then the critical angle is 3.7. Okay, and remember that delta goes as lambda squared, so as you get to higher photon energy, shorter wavelengths, this number is going to get much smaller. And then we'll talk about multi-layer mirrors. How do they, interference coatings is a more proper word, and that they, in fact, they have their reflection at the Bragg condition, and just give some examples to that, okay? So I'm not stopped now. Unless you ask a question, I'm just going to go through these last things, because they're all going to come up again. This is a reflection coating, a measurement for a very good, high-quality coating of molybdenum and silicon, so moly silicon, and it's getting to 70% at this wavelength, just here. So again, the absorption edge for silicon would be here. And we'll talk, I guess there's going to be a separate seminar on EUV lithography I was asked to do. So I'm going to do, it's a more practical discussion, but we'll talk about how that works. It works with illuminating some pattern on an otherwise reflective mask, but has an absorption pattern on it. And then there's some optical system, much more sophisticated than this, that projects a smaller image and prints patterns over and over again. the other applications of these same optics are involved in what's called the Trace telescope. Okay, so you can look at. So every time there's a solar storm on the news, I hear the word trace. Okay, it's this imaging system that's up there. It's always looking at its position, so it's always looking at the sun. It takes these beautiful images every few seconds, and the ejected particles that come out that make a solar storm here on Earth and produce extra emissions of the green light at the poles and everything. But anyway, you can see these magnetic structures that go up, and the particles follow them. And there, for instance, there's a lot of iron in the sun's atmosphere, and those iron particles, they're ionized, and they're moving, they spiral around the magnetic patterns, but they're atoms, and they release characteristic emissions. And this is an image at one of the characteristic emission lines of iron. And this is up there producing images all the time. And this is a scheme for probing materials, imaging. So here's our two KB optics with the curved surfaces. They actually have multi-layer coatings on them, which helps to select a band of radiation, and it actually also improves the resolution a little bit as a small secondary effect. But in this case, in this example, the radiation is coming from a bending magnet on a synchrotron. The optics is collecting a small amount because they're at glancing incidence, so they're not very great collectors. Okay, and they're focusing that radiation to a small spot on some sample. It could nominally be 8 or 10 kilovolts, depending on the coating on the optics, and then there's characteristic emissions. So in this one, it's a solar cell which has, unfortunately, got some iron into the solar cell. So this is from a small company who makes solar cells, and all of a sudden the solar cells are not working. They're not generating a voltage. What's gone wrong here? And there was a company in Ohio, which is far from California, but somebody told them that if they came to this place, somebody could tell them, could analyze their thing. So the fluorescent emission comes from every atom that's in there all at once, and you collect all of this radiation, and you see what atoms are there by what kind of characteristic emissions there are. And you can because there's no bremsstrahlung here, there's no electron. It's not like you shot an electron in there and it produced bremsstrahlung and characteristic radiation. Here you're coming in with a well-selected photon energy, and you're exciting fluorescent emission so it's incoming is a photon, outgoing is a photon. There's no noise level here. So it's just a matter of what's your sensitivity of your detectors and the collection solid angle. And they can detect parts per billion, femtogram quantities. And in this case, these people brought the solar cells in. It's in, because it's up around 8 kilovolts, you can do it in air. You don't have to be in vacuum. And within a day, they had all the data, and they were sent home with nice graphs. And what they had found was that all the elements that they knew were there, silicon and everything, showed up just very strongly and everything else, but iron contamination was detected. And so they're not supposed to have any iron. They just said, thank you. They went home and they looked for how this impurity was getting into the process and solved the problem. But at any rate, it's an example of using these optics. At the time, this was about a micron focal spot. People now have gotten this down below 10 nanometers. It's not the normal thing, but the group at Osaka University working in Japan at their big synchrotron facility, Spring 8, has gotten it down around 10 nanometers, actually slightly below. And then some plasma physics. So, of course, you're greatly interested in plasma physics. It's not my part to play here, but we do have a fourth lecture, which is undefined. And so we'll see what you'd like to talk about at that time. After the third lecture, we'll have a discussion about what to talk about. But these are similarly the kinds of expressions that you're interested in for characterizing a plasma. So what is the distribution function of electrons? How does that relate to temperature? the plasma, I should have started here. What is the plasma frequency? What does that mean? What is a Debye length? How many electrons in a Debye sphere? How is a temperature defined? And collision frequency, and what about some of these electromagnetic effects? What is the refractive index of a plasma? Some nonlinear effects. Where does black body radiation fit in here? I personally find black body radiation to be a terrific limiting model which you can learn so much about. You can use it. It's, you're never in equilibrium in any of these plasmas, but it's really something to pay attention to because it's so simple and it gives you some sense of what your answer is going to be and how it's going to scale. So you'll see some example in one of the lectures. And then this is about, so I think we're out of time here now, but here's an example of laser light interaction with matter. It creates the plasma itself. The plasma starts expanding into vacuum, so it comes from some high density surface into a vacuum, and so there's some low density. The interaction is around the critical electron density where the wave can no longer propagate in any further. And what's happening, where is the X-rays emitted from? How much of it is in the slightly overdense region, how much in the underdense? Depends a lot. We'll see examples in one of the EUV lithography lecture. This becomes quite important. Okay? And what is the range of temperatures and densities? And then, so how to model plasmas. So, and how to understand them. So you can understand them on different levels. On a microscopic level where you're looking at every electron in every atom, and if you try to do this, you can't track too many particles, enough. But there are some cases where you want to do that, and you actually want to track microscopically the motion of every particle and do that. And for instance, you would have probably, maybe some of you have even used some particle and cell calculations. Sometimes you don't want to know all of that detail. You want to know a little bit more about the electron distribution and temperature effects, Landau damping or other things, and you use a kinetic model. So you can go from this microscopic to a kinetic model, and in many cases you can get away with a fluid model. There are many, many things you can understand here where the parameters now are not the details of single particles, but what's the collective electron density, ion density, temperature, pressure, and velocity. And these three models of understanding things address different problems. So strongly nonlinear problems, you might want to start here. See wave breaking phenomena or something like that. There are many nonlinear problems that you look at here too. Stimulated Raman or Brillouin scattering as examples. So this is some of the mathematics. So these are the things you can't do in a lecture, but they're in the book. And this is the microscopic description. Maxwell and the Klimantovich equations, okay? And then a kinetic description of Lossoff equation, for instance, and then the fluid, the continuity and momentum equations, conservation. So I think you probably know all about such things. And how you model these things, what kind of numerical modeling you can use. These are kind of old, but they capture the idea. Some particle and cell calculations, a finite number of particles, and you look at some interesting phenomena. And or a more global approach, essentially on a fluid level, as shown here. And this is from the black body radiation, Black body is in equilibrium, and it gives off an emission spectrum that peaks at a photon energy of 2.8 times the temperature, okay? And it radiates as temperature to the fourth power. And these relationships I just find to be very useful, and I'll give some example of them later on. And now, before we were looking at the what was the energy required to ionize a neutral atom? We have an atom with so many electrons. We talked about the K edge and the L edge to pluck an electron out. But in producing a plasma, you're putting a lot of energy, whether it's with electrons or photons, electron beam or a laser beam on the target, and you strip off some outer electrons, and what's the final ionization level you get to? And there are some great advantages if you can get yourself down, if you can set your temperature depending on the atom that you've got and its binding energies, if you can match the temperature of the that you're going to produce with the binding energies, you can get closed shells. And then the spectroscopy and some other things become very interesting and interesting control. If you're trying to make a laser, a so-called X-ray laser or EUV laser, it's very important that you get all of your atoms in the same ionization state. You don't want some at Z equals Z, how many electrons are left? 15 electrons, 16 electrons, 17 electrons. Then you've got all different energy levels and you're trying to laser on them. What you really want to do is get them all into one ionization state. And this table is looking at how much energy is required for different atoms to remove an electron. So this is saying, in this example, for this atom, for argon, where it's stripped off some electrons and it's only got 11 electrons left, how much energy is required to remove that 11th electron? So this is like neon plus 1. It's like 10 would be the closed shell. It's got one extra electron. How much energy is required to remove that 11th electron? Well, it says here 143 eV is required to remove the 11th electron. That leaves you with a neon-like closed shell. And to remove that next electron, it jumps up to over 400 eV. So if you could have a temperature that's just enough to remove this guy, which by the black body radiation would be divided by 2.8 roughly, so maybe a 50 eV plasma would remove these electrons, but would not be very efficient at breaking up this neon-like outer shell. And so it's a closed shell. I call them ionization bottlenecks. It's particularly important for X-ray lasers, but there's lots of others too. And these are kinds of spectrum from a plasma. This is one of those multi-layer mirrors. So this is work. This isn't directly from the Dublin group, but Jerry O'Sullivan's group plays a major role here, okay, in this emission spectrum and characterizing it. Well, anyway, there are other. Later on in the lecture, there'll be more of this. And notice that this is around this 13.4, 13.5 eV, and this is in xenon. It turns out we want to operate with tin, which is messy. Xenon is nice and inert and clean, doesn't contaminate your optics. Okay, so this is about lasers. How do lasers work? What's the process? This is work from Jorge Roca, who's going to be here, I guess, soon to give a lecture, not in this series, but a workshop coming up. And high harmonics, which I'm not going to talk about either in this lecture. High harmonics is where you take an intense femtosecond duration laser, shine it on a bunch of atoms, ionize them, and what happens is the intensity of the incoming wave is so strong that the electric field will take one of the bound electrons, rip it off the atom. You can speak in quantum mechanically of it tunneling through, helping it to tunnel through the barrier. But basically, a very intense laser coming which has an intensity, or irradiance, that's so strong that the corresponding electric field is strong enough to pull the electron right out of the atom, and it'll start going away from the atom, but this is it's a very high frequency, and before the electron gets too far, the field reverses and it's driven back, and there's some probability it'll hit the ion left behind that it came from, and when it does, the interaction is very short in time, and it has all of that energy. The binding has the electron energy that it got in the field plus the binding energy, and it will emit photons, and all of these atoms will be doing it at the same time, and in the forward direction they interfere coherently, and you wind up getting a comb of emission of harmonics of the incoming frequency. You get harmonics, higher frequencies, higher photon energies, because that interaction was so short. When the electron got pulled off and then turned around and slammed back into the atom, the interaction was very short in duration, so small in time means big in frequency, and that's how you get the high harmonics. And so this is a great tool now, using high sapphire lasers to probe all kinds of dynamics. And the group of Krauss, for instance, Ferenc Krauss, who I guess you had speaking at your conference last week, has been leading the world, among others, in attosecond applications, producing 80 attosecond pulses and using them after they are produced here to probe the molecular dynamics, the electron dynamics in molecules. So it's a very interesting area. And there's issues of coherence. What is coherence? What's spatial coherence? What's temporal coherence? Well, I'll talk a little bit about that. So there's a longitudinal coherence. What is the line width? How well do you have to match paths? But there's also spatial coherence. And it's good to understand how those things separate. This is from, I'm really out of time now. This is from Arthur Charlow. It was in Scientific American. And it shows a light bulb with a distributed source and a very broad bandwidth. It's a light bulb. It's a white light going in all directions. But if you put a pinhole in front of it, you can do spatial filtering. And if you put a filter, you can do monochromatization, choose a wavelength. So longitudinal coherence. So spatial and temporal coherence, and you can combine them. And with a light bulb, you can make coherent light. And for instance, another short story. So at a certain point, I was trained in plasma physics, but I was working in laser fusion, and I was really interested in lasers and holography and all of these things. And at a certain point, I had never seen this. It struck me that I could make holograms with incoherent light, with these tricks. And I thought, oh my God, I'm really onto something here. So I went to the library and did a library search, and the printout was incredibly long about all the people who were using this technique, which I thought I'd discovered something, but not to be the case. Okay, so we'll talk about zone plates and microscopy. This is what a zone plate looks like. This is the circular diffraction pattern that's used for focusing radiation to very small spots or for imaging. So the highest resolution imaging currently comes with such structures. We'll talk about how they work, use the Pythagorean formula, and you'll see that there's a positive interference effect here if the zones satisfy this relationship. So it winds up that all you need to know is Pythagorean formula. That's good. And this is the size of what one looks like. Here's the zone plate, and here's a human hair. So this one has a diameter of 86 microns. There's some that are even smaller. And some variations of this. There's the simple zone plate, but one of my colleagues here has gotten into all kinds of absolutely weird-looking zone plates that have some special function. Okay, this one helps you to produce an interferometer. This one helps you to introduce angular momentum, being used now in some really interesting medical experiments, but also you could imagine it for some of these magnetic probings where you need a certain angular momentum. This weird one, in microscopy, high-resolution microscopy of single cells now, is used for tomography to get three-dimensional imaging with these zone plates. But it turns out that the resolution is not set by the zone plate itself. It's usually the outer zone width, approximately, would set the resolution. So if you use the zone plate with 20 nanometers outer zone width, that's approximately the resolution you're going to get. But there's a depth of focus issue here. And in even looking at a single cell, which has a depth of maybe 10, 20, 30 microns, the resolution, the three-dimensional resolution from tomography, the object is rotated and you keep taking images, the reconstruction is limited by the depth of focus. Not by the resolution of the optic itself, but by the depth of field, really. And so this particular zone plate, all of these come from one person who's now at Stanford, and this introduces an aberration. It's a cubic zone plate. It's put there because it introduces an aberration. If an optic is aberrated, it doesn't focus as well. So the depth of field gets increased with a lousy resolution, but it gets increased. Now, if you know what the aberration was that you put in there that increased this thing, you can correct it. Well, she can correct it. I can't correct it. And so she then goes plane by plane and does the correction. and can increase the depth of field effectively by correcting the aberration plane by plane and getting back the best resolution. She uses this cubic zone plate. And this is the lithography thing that we talked about before. The main issue for the lithography is the plasma source. So if you're interested in plasmas, this is a place where people are very actively pursuing this, and we'll have some comments to make on that. And this is in this EUV lithography. This is the tool that actually prints the pattern. It's called a stepper. I'll explain why it's called a stepper. And this is from ASM Lithography, the Dutch company. And it's not as big as this room this way, but it's like a small camping trailer that you might use. So it's fairly big. That's it. Yeah. So we're gonna. So I guess we're ready for some lunch.
Ready?
Yeah, I think so. So thank you very much for a really brilliant introductory lecture. So we'll be having lunch. It's outside, and we're aiming to be back here for about 2 o'clock, I think. Thank you.
All right.